Hi there, I'm Tom Goro, President of the Global Coral Reef Alliance, and I'm here to talk about why carbon lives matter, how to harmonize the costs and prices of carbon trading with the lifetime of carbon. This is the missing element in all carbon accounting, and it's a fatal flaw that prevents the climate change treaty from achieving its own goals. Carbon is the common currency of all forms of life on Earth, of all the energy we use. It drives our climate, and carbon transfers drive all of our economics. The atmospheric CO2 is the measure of the amount of carbon, and that's what's causing climate change. It's the result of all these other processes happening simultaneously. We can't control CO2 unless we account for the costs and the prices. So there's definitely around the world, we're moving towards some sort of form of carbon trading and carbon credits to manage the climate emergency, but no one knows how to price carbon properly, and that's the focus of this talk. The problem is that everyone assumes when they trade carbon that carbon is fungible, like money is. And that leads to completely distorted outcomes because they don't take the lifetime of the carbon sources and sinks into account. So we're going to show here how carbon fluxes in and out of the atmosphere can be weighted by their lifetimes to ensure that there's accurate climate accounting so that the climate change treaty can meet its own goals. Here's a problem we face. We've just been through COVID. We're in the middle of COVID, as a matter of fact, and we found that we had to suppress the rate of COVID spread in order to prevent a catastrophic decline of our health system. We're ignoring the climate change issue. That curve we're not flattening. That's racing away. In fact, COVID didn't even slow down the increase of CO2 in the atmosphere. It's racing ahead, and as this graph shows, it's accelerating. Well after COVID will be over, it'll still be accelerating. So the question is, how long will that happen? This is a figure from the Intergovernmental Panel on Climate Change that they rarely show. And the reason is this shows 3,200 years, or 3,000 about that, of response to climate change. And what it shows is that even if we bring CO2 down to net zero, and here you see the CO2 emissions, the black curve, coming down to zero. Here they're taking, in this figure, 200 years to get to net zero, which is something we cannot afford. But at any rate, the point is, whenever you get to net zero, at that point, the CO2 concentration in the atmosphere levels off. It doesn't decrease, it stays high at that point. Average global temperature will continue to rise even after CO2 is stabilized because there is heat in the pipeline. The deep ocean has been absorbing heat. 93% of the heat that the Earth absorbs goes into the ocean, so we're not feeling the effects at the surface. If all the heat that had gone into the ocean had gone into the atmosphere instead, surface temperatures would have risen by 36 degrees Celsius. I mean, it's just shocking that that's because the heat has gone into the deep sea, but it hasn't disappeared. It's slowly circulating, and the ocean takes 1,500 years to turn over, so that heat will come back to us in about 1,500 years. So that's why, even after CO2 levels in this graph, the temperature still continues to slowly rise, and that continues for about 1,500 years. That's longer than the scale here on this graph. Now, the other curves that you see here are the rise of sea level due to the expansion of water as it gets warmer and due to ice melting. As what you see here in this graph is that the rate of sea level rise due to melting of ice is still accelerating 1,000 years after net zero has been achieved with CO2. So that's being ignored completely. And that would lead up to about 80 meters more sea level rise. But we don't hear about this. We only hear about a meter or two because IPCC has focused all its projections in the very beginnings of this curve, the first 100 years, and they've ignored all the rest. They've ignored all the long-term impacts because that wasn't what they were responsible for predicting. They were only asked to predict short-term impacts. Everyone thinks that when those are over, that's it. But no, they will continue to rise for thousands of years afterwards. So it's a very serious issue. To control CO2, we have to look at the global carbon cycle. Global carbon cycle is very complicated, but there are some simple features of it. The first thing is to realize is that soil organic carbon is about the biggest pool that's accessible of organic carbon. And we're wiping that out. We've wiped out photosynthesis, the land vegetation, we're destroying the sea. So all the natural exchanges of CO2 between photosynthesis and respiration, exchanges with the ocean, those are going down while fossil fuel combustion is going up. Forest destruction is still high, although once the Amazon is gone, there won't be much left to destroy. So that's decreasing. But the point is that what we have now is a situation where we have a dangerous excess of CO2 in the atmosphere. That's the red part. That's about 40% too high. To stabilize climate at safe levels, we need to be at pre-industrial CO2 levels. And that means this dangerous red excess has to be removed. There are various proposals on how to do that. Some people propose shooting it into space or making big mirrors or sucking it up with machines, but none of those approaches, so-called geoengineering, are yet practical or proven, and certainly none of them are cost-effective. They'll be very expensive. So we're proposing is really that the quickest way to remove that excess CO2 is to grow plants to absorb it and then put it into the soil, where all of that excess could be increased with only a small increase in soil carbon. So that's what we think is the easiest way to do it. Now, a carbon market doesn't work very well. This shows the EU carbon market price. As you can see, it's ranged between about $0 and $30 a ton, and it's still too low to pay for carbon removal by any of the standard geoengineering methods. So this is a clear indication of total failure of accounting. They don't account for the carbon sources and sinks, and they've got the price totally erratic. So this is not the way we can go. Part of the problem is that they think that carbon is fungible. And we say that's not the case. You have to consider each carbon sink by how long that carbon will be kept out of the atmosphere. The key issue is the lifetime that is kept from recycling and getting back into the atmosphere. And in the same way, the sources should be weighted by how long that carbon has been kept out of the atmosphere. So therefore, carbon costs and prices should be measured in carbon ton years. And so we need to multiply the amount by the lifetime. And that's missing from standard accounting. Now, in order to solve the climate change problem, when we take some source of carbon and put it into the atmosphere and then try to remove it, the sink should last longer than the source out of the atmosphere. We're trying to remove CO2. So it makes no sense to take coal that has been buried in the ground for 300 million years, turn it into CO2, spend a lot of money to concentrate that carbon dioxide, and then pump it into Coca-Cola or Pepsi-Cola, where it will fizz right out into the atmosphere. So it might last, minutes after you open the bottle. So to take 300 million year old fossil fuel and call that a carbon sink is a fraud. It's a temporary and ephemeral sink. And there are many such proposed. The whole field of carbon credits, those people peddling carbon credits, many of which are fake or ephemeral. Let me give one example. Photosynthesis or fertilization of the sea is proposed as a carbon sink. People say they'll spread fertilizer all over the ocean, and then phytoplankton will grow and suck up the CO2. But in fact, your average phytoplankton lasts 1 day or 2 days before it's eaten, before it respires the CO2, or before viruses kill. It turns right back into CO2 in about a day or two. That carbon is then recycled for about a year before it falls out of the system. But the point is, then it's only being delayed by a year. And if that carbon sinks into the deep sea, that'll be recycled again. But then it'll take 1,000 years to get back to the surface. At least you've introduced a 1,000-year time lag, but that doesn't compensate for a 300 million year old coal. You'd have to do that thousands and thousands of times over to compensate for the loss of carbon storage it would cause by burning that coal. So the lifetime is really key. The sinks that have the longest lifetime are going to be in the rocks, limestone, organic carbon in sediments, and black carbon, or like biochar. These things last hundreds of millions of years, so that really preserves it. So what we're going to do here is take a look at CO2 residence times. This is all the different sources and sinks of CO2. And the key thing is that all the carbon dioxide in the atmosphere is cycled in about 3 years. There's an imbalance. The sources are larger than the sinks, so that's why it's doubling in about 100 years. But the big ones here are photosynthesis. Photosynthesis cycles all the carbon CO2 in the atmosphere in 6 years. Then it gets released back through respiration. The ocean takes about 7 years to cycle. That gets absorbed by the winds and waves and then released back out. So there's a very active cycle here. When we rank all of the sources and sinks on a time scale, you'll see how large the range of ages are. Ranges from 1 year to 100 billion years. So there's a factor of 100 billion in these time scales here. So what I'm showing here in the central column are the sources of CO2 and how long the residence time of those sources are. The residence time is how long it takes for that source alone to double the amount of CO2. So volcanism, CO2 would take about 10,000 years to double CO2. Fossil fuels and deforestation, which are unbalanced, and we mark them in yellow because they're human-caused sources, those take about 100 years to double CO2 in the atmosphere. But the much faster ones with the shortest residence time here are the ocean atmosphere and photosynthesis and respiration. Those are normally in balance, and those cycle the carbon very quickly. So what we need to do really is to try to increase the long-term sinks, which are the limestone and organic carbon in the sediments, or alkalinity or weathering. That alkalinity lasts about 100,000 years, so that's not as long as coal or oil. But let's take a look at the age of fuels. If we burned grass that has grew this year, it would be 1 year old. If we take your average wood, it might be a few decades, typically. Peat is in the range of thousands of years old. But natural gas and petroleum, those are about 50, 60, 80 million years of average age, and the average age of coal is about 300 million years. So in other words, if we're trying to alleviate the effects of fossil fuel carbon that has been stored for tens to hundreds of millions of years, we have to put them into sinks that are going to last as long. Dealing with these ones low down is not going to do it. However, these sinks are very slow to accumulate. They last for a long time, but they accumulate slowly. That's why they have a long residence time. So let's discuss now how we can increase the carbon flow in order to put more carbon in the ground. One method is what we call regenerative soil carbon management. And this shows different methods of soil carbon management, showing the tons of carbon per hectare incorporated into the soil. The first column is ordinary agriculture, where your farmer grows wheat or corn or something else and plows the residue into the ground. And they tend to put in, roughly about 3 tons of carbon per hectare per year. But with more advanced methods of land management that recycle the carbon, they put in livestock and trees, you can get tens of tons of carbon per year. So that's the high end. The people who are really putting carbon into the ground are doing amazingly well, but the problem is most farmers are doing very poorly. So what we need to consider is what the best practices are and how we can expand them on a global scale, because what we're doing now isn't working. What we're doing is we're running down the carbon in the soil and the vegetation. We've lost about half of them already. So this shows some ways that we can increase productivity in soil. This is biochar, which is black carbon, which was invented by Amazonian Indians thousands of years ago, and it's elemental carbon. It holds on to water and nutrients and carbon in the soil. It lasts forever in the soil. And when you add biochar, biochar is like charcoal, but you can either use the raw stuff, which is shown in red, and that kills the plant. It decreases the growth rate. But the blue is a mature biochar. That's been mixed with compost and allowed to age and build up nutrients. So with that biochar, which goes from about more than double the growth rate with good biochar, whereas the bad biochar reduces the growth rate by about 3 times. So biochar is one way you can do that. And biochar is carbon that essentially does not degrade. It takes centuries to thousands to millions of years to degrade. They are forest fire charcoal that is 350 million years old that are perfectly preserved. You can see every cell in the tree that burned. So biochar works. The other thing that works is remineralizing soils. This is data from a site in Panama on some of the worst soils in the country. Once they cut the jungle down, there's just almost nothing grew, sparse grass in clumps. The soil was very infertile. What we did is we grew trees there in basalt powder from a quarry and compared them to local soils. And what you see here, just by adding basalt powder, we got the trees to grow nearly 7 times faster, with great increases in phosphorus and iron and all the other valuable nutrient elements that are missing from the soil were increased to that. Now, we could have got trees to grow even faster if we'd also added biochar and compost, but this was just basalt powder alone. So the point is, with scientifically sound land management and regenerative management, we can greatly increase productivity. We can put more carbon into the ground. Then the question is how to hold it. So this shows graphs of how quickly we can build up soil carbon as a function of how quickly we draw it down, tons of carbon per hectare per year, and as the proportion of long-lived carbon, like biochar. Some carbon, like sugar, decomposes very quickly. It'll be eaten up by bacteria in days. Black carbon will last hundreds of millions of years. So what we see here is we saw that typical farmers are drawing down only about 3 tons per hectare per year, and they're only getting about 1% black carbon in their soil. And so under those circumstances, it would take more than 1,000 years to draw down CO2 by increasing the carbon in the soil. But on the other hand, if we now go to what the best farmers are doing, this is the tens of tons per hectare per year, and if we increase the amount of biochar in the soil, literally you could do this within years. I mean, that's the best case scenario. That means all the farmers everywhere in the world using best practices, which isn't likely. But the point is that if the bad practices will take thousands of years to make any difference. If we use our best practice, it can be done very much more quickly, as quickly as we choose to do it. So that's one way that we can be storing carbon much more, that lasts much longer. The longer we wait, the more difficult and expensive it will be to stabilize climate at safe levels. And we're already getting to the point where it's going to be impossible soon without actively removing carbon from the atmosphere. So the point is that using what we call geotherapy, or stimulating the natural mechanisms that control CO2, is vastly cheaper than using expensive machines to do that. But the longer we wait, the more difficult and expensive it becomes, to the point comes that it's utterly impossible to do. And we're getting to that point very soon. So I want to mention one other method. One thing we can do is store carbon in soil and make sure it's in forms of carbon that will last for a long, long time. The other thing we can do is in the ocean. We have developed a technology called biorock technology. We use safe, low-voltage electricity, like what you get from solar panels. What we do with that is we grow limestone rock in the ocean. That lasts hundreds of millions of years. It doesn't disappear. We produce huge amounts of biomass. We grow all marine ecosystems much faster, so they have much more organic carbon. And we accumulate the sediment organic carbon in the soils of seagrass, salt marshes, and mangroves. So that's where, with electricity, in fact, surprising as it seems, we're able to produce the longest lasting carbon sinks, and at the lowest cost. There are 3 methods that we do that. One is that electrolysis of seawater grows solid limestone building materials that are 2 to 3 times harder than concrete. And they're carbon neutral. They don't produce net carbon. We can also grow carbon negative cements that are even harder than that. And that can replace Portland cement. Each ton of Portland cement that's produced releases a ton of CO2. And that's the most common building material in the world. It's 8 or 10% of all human fossil fuel sources are coming from concrete. But we can replace that with better, harder material. And what's interesting is we can produce this material at about 1 ton a megawatt hour. Depends on the cost of electricity. The cost of electricity is 10 cents a kilowatt hour, then that'll be $10 a ton. If it's only down to 1 cent a kilowatt hour, and that's where we're getting with solar energy now, it'll cost you $1 a ton to produce that. That's vastly cheaper than cement, as well as sequestering CO2 instead of producing, as well as being harder. And we can grow that naturally in the sea. So that's one way that we can produce carbon negative building materials and eliminate carbon positive building materials. In addition, we grow back living reefs, and those regenerate the ecosystem services, the fisheries, the beaches that had washed away reappear in months. They grow right back. And we protect coastlines from rising sea level. We haven't talked about rising sea level, but the fact is about 1.5 million kilometers of coastline that need to be protected. Half the beaches in the world are going to wash away in this century, and that's if sea level rise and storm strength do not increase. So they're going to disappear more quickly than that. And as I say, if we don't control global warming, we have about 80 meters of sea level rise ahead of us. With biorock, we can grow back coral reefs and grow back the beaches, and the biorock grows upwards, rock hard, faster than sea level rise. So these reefs will keep pace with sea level rise. They won't be overtopped the way a rock or concrete wall would cost. And they cost about 10 times less than a rock or concrete wall that does not regenerate the fisheries and the seagrasses and the salt marshes and store carbon. So the final way we want to remove carbon is as blue carbon. And this is also going to be very cheap. These are growing seagrass, salt marsh, and mangroves. We've destroyed half of those ecosystems in the world already. That CO2 has gone into the atmosphere. But if we grow those back, we can absorb CO2, and we can make them grow even faster with what we know, and make them absorb and retain more CO2. So the point is that blue carbon, biorock electrolysis, regenerating marine ecosystems is probably going to be among the cheapest carbon sinks that we have. They're long-lasting, and we'll save a lot of money if we do it. So there are methods to solve the problem if we have the will to. Here are some photographs of biorock structures. In the upper left are limestone 2 to 3 times harder than concrete that we grew in the Maldives. Upper right is a 4-year-old biorock reef in an area that was barren. It had sand and a few little pieces of broken coral. There were no fish, no living corals. We put a few corals on, they grew like mad, and everything else settled and came by itself. That's after 4 years. The lower left is a salt marsh we grew in New York City with a solar panel in a toxic waste dump in New York City, a Superfund toxic waste site. So we're able to grow this seagrass. Right now, all the seagrass, salt marshes, are eroding away because of sea level rise, but we're able to grow them towards the ocean because we get such prolific root growth, such tremendous underground growth. We're storing carbon in roots as organic matter. And at this particular location, we built up about 5 or 10 centimeters of mussels, shells that are growing clumped around the grasses, so greatly increase the growth. On the right-hand side is a new biorock reef. It's just turning white, growing limestone, and it stimulated the growth of the seagrass all around it, which is another carbon sink. This is the very beginning of it, but this project now is covered with corals that settled on it by themselves. It's full of fish, and the beach that had washed away that's behind it grew back in about a few months. So there are solutions, regenerative solutions, to store carbon that provide economic and ecosystem benefits. Carbon lives don't matter, and politicians won't account for carbon honestly. We're all fried. The point is that this dishonest accounting that has caused this problem, if we don't learn to count carbon properly, we're in deep trouble. Thank you.